Light reflects and refracts in a certain way. A ball thrown into the air follows a parabola. And me, well, I'm lazy. The reason behind all these is the principle of least action, the simple observation that objects tend to move in a way that minimizes a certain action. And believe it or not, all that we know in physics can be derived from this simple principle. So, what exactly is action? Well, action is an abstract quantity. Intuitively, a path with greater action is less efficient. You might think of action as the difficulty rating of a hiking trail. Imagine slicing the path into infinitesimal slices. The action of the whole path is the sum of the individual actions of each of those slices in the path, much like how the difficulty rating of a hiking trail is the sum of every little part in it. So, how do we find the action of those minuscule slices? Well, we use something called a Lagrangian, which we can define according to the dynamics of a system. The Lagrangian function, together with the Euler-Lagrange equations, enables physicists to find the path of least action in a system. Now, let's take optics as a simplified example for the principle of least action. Action here is defined as the time it takes for light to travel a certain path. In minimizing this action, we get the laws of diffraction. Why? Suppose a ship is sinking out there. How can I get there quickest? Well, of course, I could go in a straight line. But wait, I'd rather cover a little more distance by running so that I can swim less, because I run faster than I swim. Light does exactly the same thing. It travels quicker in air than in water, and therefore it bends to get here. And that's why we see diffraction. Suppose I want to shoot this basketball. Why does it have to travel in a parabola? Yes, you guessed it. It's the path of least action. Now, action here is the sum of the kinetic energy minus the gravitational potential energy of the ball at every moment in its path. The parabola that the ball travels in has been shown to minimize this action. To generalize this, all objects under the influence of a gravitational field move in the path of least action. These are just the beginning. The principle of least action offers a new and powerful approach to writing the laws of nature. Not only is it more concise and elegant, it also remains in the same form regardless of the coordinate system. This makes it invaluable when dealing with subjects like relativity. It also plays a huge role in contemporary physics. The Lagrangian is among the easiest ways of formulating the standard model, while the Einstein-Hilbert action gives us the dynamics of gravity in general relativity. Even now, it is helping research in M-theory. It is simply awe-inspiring that at the heart of nature lies such staggering simplicity. As complex as the world is, there's always a simpler form of reality, and it's up to us to uncover it.